In this video, we're going to look at the implementation of graph matching. We'll have a look at suitors and sorting. For the implementation, we need a data structure that stores the vertices, information on the vertices, and information on the edges, everything that's needed to run the algorithm. And for an edge, we need to store its weight. And for a vertex, we store two values. First of all, we store the preference of a vertex v, which is the preferred partner. That's the neighboring vertex with the highest weight. And we also store the suitor, which is the neighboring vertex that with the highest weight that prefers u, that prefers v. The preference and the suitor, they are initialized to nil. At the start of the algorithm, they are nil. We assume, to keep the algorithm simple for the time being, that there are no ties. So there's a unique preference that a vertex has, and also suitors are unique. If we have a preference and a suitor for a vertex v, then it must hold that the weight of the connection between v and its preference, it must be higher than or equal than the weight of the connection between the vertex and its suitor. Because if it would be less, then the suitor would be the preferred partner of v. So that's why this has to hold. During the algorithm, what we do is basically setting preferences and resetting them. And here we see one of the possible situations, that is when a vertex sets a preference, v sets a preference to u, but u already has set a preference to v. In that case, you discover at this point that the preference is mutual. We have a match shown in black. So u and v are registered as matched. On the other hand, the suitor x of u doesn't have its preference anymore because it got matched. And so it has to again set its preference, a new preference. It can also happen that you set a preference, v sets the preference to u with a weight of 9, but u has already set its preference with a weight of 10 to another vertex. And that means that v can set its preference to u, but it's not mutual. We don't have a match. And in this case, u already has a suitor with a lower weight. The suitor is x. So x will be displaced by the higher value, and in this case v becomes the new suitor. X has to reset its preference also in this case. And then there's the dreaded situation where you get an immediate rejection, and that is because in this case you set a preference, v sets a preference to u, but the preference is lower than the value of the current suitor. This also means that we can remove the edge u, v. My question to you is, why can we remove it? The answer is that unfortunately u will never match to v, so we can remove it. And the reason is that although u at the moment has a different preference, at the point that u loses its preference and resets its preference, it can set it to the value of 9, and it will never match with v. So that's why we can remove it. the edge is dead. Every vertex has an adjacency set. It's the set of edges that are connected to V. We denote it by adj V, adjacency set of V. And you can store it just as a list. For example, a list with the vertex numbers. The list has length d, that's the degree of V, the number of neighbors. If we store it that way, this looks very much like the compressed row storage of a sparse matrix, where the neighbors in the graph are really the non-zeros in that particular row of the matrix. This is the case for the compressed row storage for symmetric matrices, because we have an undirected graph. All the lists together of the vertices, they can be stored in an array of length 2m, where m is the number of edges of the graph. And the reason is that if we add up all the degrees, which are the lengths of the adjacency lists of the whole graph, then we get 2 times m, because every edge counts twice. It has 2 endpoints, and both count in the degrees. So that's also the amount of memory we need for all the adjacency lists together. So here is the local domination algorithm, where we have in our implementation the suitors. And we initialize it, that's what you see here. We have a matching set M, which is empty at the beginning. We also have a Q, a set of vertices for which we need to set the preference. So initially, we need to set all preferences. So Q equals V. And you see we have initialized the suitor and pref values of every vertex to 0. Now you have some freedom in how to implement Q, what data structure to choose, because Q represents the work of the algorithm. It's the vertices for which we have to set a preference. Now you can decide to implement it as a queue, where you take it from the first in, first out. So you reset the preference only after everybody has had his chance, or you can also use it as a stack, meaning last in, first out. So the last one that lost its preference gets immediately a new preference. That's a different approach. It gives different algorithms, really. This is the main loop of the algorithm. It has several parts. What we do, the main loop is really pick a vertex V from Q, remove it from Q, and then set a preference if dV, the degree, is larger than 0. Because if the degree is 0, it means that the adjacency list has become empty. Now, if it's not empty, then you find a preference, and you search for the preference. The preference becomes UV, that's the edge. So U is the vertex that is connected to V. U is the preferred one of V. And you search in the whole array between 0 and dV minus 1, all indices. And then once you've found it, you can reduce the size of the array. So dV decrements with 1. Then we assume that you have succeeded, because if not, you could have removed something from the adjacency list. So we get a new suitor, and we need to remember the old suitor, X, and add it to the Q, because it has to set again its preference. V becomes the suitor of U, and if it's mutual, if U is the suitor of V, then we have a match and register it. And once we do that, we can set the degrees of both U and V to 0 because they are out of it, and so the adjacency list can be considered empty. A little trick to improve the speed of searching for the preference is to do partial sorting. So what is partial sorting? We have an adjacency list. We take a random value and we split the list into everything smaller and larger than this random value. And that value is a splitter. So xi is less than xr for all I less than r. And it's xj is larger for all j larger than or equal to r. And that means that we only need to, if we have such a splitter, we only need to look for all the xj with j larger than or equal to r. We don't have to search the whole array again. And that is helpful. So how does this change the algorithm? You see that first we find a splitter r, and then we don't look for a preference in the whole array from 0 to dv minus 1, but only from r to dv minus 1. And then after we've done this, we split the adjacency, we split that part again. So that is for future preferences. The idea is that if you go once through your data, then you can do that again. And then in the future, you only have to go through half the data. The computation time of this algorithm. The initialization, at most the number of vertices plus the number of edges, m plus n, is the cost. But during the algorithm, during the main loop, it can happen that you remove a vertex v from the queue and put nothing back. Or you put something back, and that is the loser x. But that means that the edge between a certain u and x is removed, because u gets a better suitor. So in any case, one of the two gets removed. And so in the end, the total cost is at most m plus n. And the computation time of the whole algorithm, excluding the sorting, is order m plus n, which is linear, and that's the best we can hope for. Now the partial sorting. We use a random splitter, and we split an array into two parts, and we may not need to split this part again, but only that part into smaller parts. So it can happen that we only split the higher parts and not the lower parts. On the other hand, if we have to split everything again, in the end, we get the quicksort algorithm, but not for all the vertices or edges, only for a single adjacency list. So the cost for all vertices together is quicksort costs like n log n. Here we get the sum of dv log dv. And if we assume that the largest degree is bounded by a delta, then this sum is less than the sum over v of dv log delta. And since the sum of all the degrees of a graph is 2 times the edges, is 2m, we get an expression 2m log delta. So if delta is small, this is almost linear. In the favorable case, where we don't need to do a full quicksort, but we never have to split a high part again, a low part again, then we halve the size, dv, half dv, a quarter of dv, etc. And if we add that up, it's only 2 times the degree that we have to do. So then we're also in a linear situation. And in practice, this happens a lot. Okay, so let's summarize what we've learned in this video. You can store a graph efficiently using adjacency lists. And the algorithm that we get is based on local domination, and that means we repeatedly set preferences for a vertex. We match if the preferences are mutual. The suitor is the vertex that prefers you and that has the highest weight, and that can be used, for example, to immediately reject a preference, and that speeds up the algorithm. The sorting of adjacency lists, partial sorting, helps in speeding up the algorithm as well, because future setting of preferences goes faster. The final question, this is the graph that we saw also in an earlier video. You are asked to set the preference for all the vertices in this graph. Once you've done that, you set all the suitors. And another question is, how would immediate rejection speed up the process?